So Mars is really old. Mars is really old. I have in this paper it's 21.33 to 30.65 billion years old. Really, really old. And if you want to adjust the Earth's age from 4.5 billion up to 10 billion or whatever, you can then be more consistent. And I got this recommendation from somebody to make it as EA or Earth age, Earth ages. So I have Mars as 4.74 to 6.81 times older than the Earth. So if Earth turns out to be older than 4.5 billion, we can still use that, and it's somewhat consistent. I got a little picture here of, well, I wouldn't say picture, I would say a representation, because if this was actually real, we'd be in trouble. Here's Earth, here's Mars. Earth 4.5 billion, Mars 21.33 to 30.62, and then the moon is just, oh gosh, I gotta believe that the moon is just this old fart. It's just extremely, extremely, extremely old. Far, far older than the Earth, far, far older than Mars, more than likely older than Venus. And Venus is extremely old. And the idea that I wanted to share is we got to start using the transformation curve somehow, and I have to start placing the mass on the y-axis, because if I don't have like a y-axis there, then it's just like it's all scattershot. And I like the idea of it being scattershot in the beginning, but now it's like maybe I should put masses there to make things a little bit more understandable, because I ran into a problem here. If you have Earth this size and you have Mars that size, how much could we figure this outer material is ripped away before it gets to be that size and is ablated away over time? Do you suppose that this material could be ablated away over a period of 15 to 20, 25 billion years? Maybe. I don't know. But that raises an important question. With transformation curves, now, this is my my 5-year-old line drawing skills. You have Charlie 1, Charlie 2, Charlie 3. Charlie 1 would make Earth really massive, and when it goes down a transformation curve, it would be both larger than Mars when it hits Mars's stage of evolution, which is down here, and it would probably be around maybe Venus size, maybe a little bit bigger, maybe a little bit smaller. Charlie 2 would be a little bit less massive, and that would also be larger than Mars. As it goes down, it would go off into who knows land. And if it's a lot smaller, which I don't think it is, that's why I crossed it out, and its transformation curve would just go off into another land as well. But that would mean if I place Earth up here, or down here I should say, it would be smaller than Mars's current stage, which means that it couldn't have had all that rock to get in the way, to ablate away to begin with. It had to have been a lot smaller, meaning the gas giant, which was forming it, had to have only collected a little bit of material at the very edges of the Taylor threshold, which is down around here. And I think that's an extreme example. I don't think Earth is, dare I say, below average. I want to believe that Earth is an average object with average people on it. Because, well, to be honest, the likelihood in a statistical distribution of being average out of 200 billion solar systems in our galaxy is much higher. We're probably leaning towards the average. The lower ends and the higher ends of that green area would be more rare. So more rare up here, and as you go down, more rare. That's given the object has the ability to host life. Clearly, there's a lot more objects down here which never formed life at all, and these completely outnumber the ones that formed life. Of course, the ones that form life, though given enough time, there's a lot more of those wandering around and smashing up and becoming, large asteroids and meteors and meteorites and all that kind of stuff. And another point, I didn't know at first when I realized the Earth is an ancient star. I didn't know that astronomers had to work inside of an idea, which is called a paradigm, and they have to make all their evidence, everything they see, everything that they observe, every measurement, all the data they collect, they have to make it all conform to a paradigm. And a paradigm is a worldview that things are this specific way. And if there's anything that's out of the ordinary, then it should be either ignored or explained away inside of the paradigm. And that's extremely dangerous during a time when we find objects that are just not conforming to the paradigm at all, because in the paradigm, what do you mean it doesn't fit anywhere? What do you mean this observation is anomalous? What do you mean this object orbiting so close to its host, such as the hot Jupiter, is an impossible object? And they use those phrases a lot in the science programming and the science articles where the scientists are, they're shocked, or they're surprised, or they're baffled. The B word they use a lot. They use the baffled word a lot. And it shouldn't really be any surprise that they will be baffled, because they're using a paradigm that just doesn't make any sense. And the reason why I had that center line going down, if you noticed before, this is the Big Bang line, I should say. The Big Bang line goes directly down the center, and it forces everything in the universe to be 13.8 billion years old. So absolutely nothing inside of the Big Bang paradigm can be on this side of the diagram. It all has to be over here. And as you can see, if the paradigm sits there and says that none of this exists, then you have to replace the paradigm. You can't keep something that doesn't, I should say, you can't keep an overreaching worldview that, in order to work, has to ignore a hell of a lot of observations. If you have to ignore observations to keep the paradigm, then you have to get rid of the paradigm. You have to replace it with something else. And in the Big Bang paradigm, as you can see here, Mars should not exist, Venus should not exist, and the vast majority of all the asteroids, of all the meteoroids, of all the gas and dust in the universe shouldn't even exist, because it's too old. It's older than what they claim the universe is. I don't know how else to explain that. And if people want to say, oh well, it's impossible for these objects, Mars, Venus, to be this old. Well, the new paradigm that we've been stumbling upon is completely okay with it, because the periodic table has what are called stable isotopes of elements. So the isotopes have never been observed to decay. So, for instance, hydrogen and deuterium are stable. They've never been observed to radioactively decay, which means you could have a whole bunch of hydrogen and deuterium in a big box for trillions and trillions and trillions and trillions of years, and it will be completely the same hydrogen and deuterium you started off with. Infinite in age. So the idea that Venus and Mars could be those ages, well, clearly they're just made up a whole bunch of stable isotopes. And the oldest material we should be finding in the universe should be composed of mostly stable isotopes. And that's exactly what we find. In meteorites, the iron and nickel in there are composed of stable isotopes of iron and nickel. It's really that simple. And the iron and nickel that they find was collected inside the star and was smashed up, disintegrated over many billions of years, and is just wandering the galaxy to be recycled into these objects. So I didn't really want to talk about Big Bang because it's turning out to be a big mess. All right, you guys, have a good weekend, and hopefully this helps you understand what we're looking at better at the night sky. Later.